the first thing you need to do when having a problem is to identify all the variables in it. And this is a problem I really struggled with on the first quiz. So I think the easiest way to solve this problem is to go ahead and write out all the variables before you even start looking at the problem. So it's initially at rest. So the initial velocity is 0. And it's fired upward. So I'm going to draw a picture. Here's a rocket. And it's fired upward. And the acceleration equals 12.0 meters a second squared. Should be meters per second. And then the altitude of 1 kilometer. So the change in distance is 1 kilometer, but we need this to be in meters. So that would be 1,000 meters. Okay. And so we don't have to worry about friction in this problem. So the first thing we need to figure out is how fast the rocket is traveling. And we already identified all these variables and when the engine cuts off. So it wants us to find the final velocity. So I'm going to write here final velocity and put a question mark. Alright, so this way, if I write it out this way, I can see all my variables and all my numbers, so I'll have an easier time plugging it into the problem. And if we look at our formula sheet, the equation we need is the final velocity squared equals the initial velocity squared plus 2 the acceleration and then the change in x, which in this case is just our change in distance. So the final velocity is, we just need to plug all this in. I'm going to move the square root over here, so make it square root vi squared plus 2a change in x. So we just plug in our numbers, and that gives us the initial velocity is 0 squared plus 2, acceleration is 12, and then 1,000 meters. So, and then if we type that in the calculator, it will give us 155, and then we can't forget the units, meters per second. There we go. And then the second part of the problem, the maximum height it reaches before falling back. So we need to find the height it gets up to. So first thing we need to do is use our final velocity as our initial velocity, since this is when the rockets, the engine cuts off. So initial velocity and then this is the acceleration. We can't use this acceleration because that's with the rockets. So the only acceleration acting upon this rocket right now is gravity. And so that should be, the acceleration of gravity is 9.8. But if we look at our little drawing over here, the rocket's going up, but gravity is obviously going down. So we have to make this a negative. And that's one other problem I had on the quiz is I should have drawn some pictures so that way it's easier to visualize the problem. Anyway, the final velocity is 0 because once it reaches that peak it's going to stop moving. And then we want to find the distance, or we can just say change in x. And so we can plug in, use the same equation before and just plug in the variables. And then we can solve for the change in x. So we're going to move this stuff to the other side. So let's subtract the initial velocity squared. And then if we subtract that, we need to divide by the 2a. So all over 2a equals the change in x. So if we plug this in, it should equal 0 squared minus 155 squared over 2 times negative 9.8. And then that, if we put in our calculator, equals 1,225 meters. And we want to find, after the free falling, the rocket's velocity right before it hits Earth. So we want to find the final velocity. And we know the initial velocity since it starts after free falling, which means it's not moving. So the initial velocity is 0. And then acceleration is just the same. It's only accelerating due to gravity. And then the distance, this part's kind of tricky. I messed up a couple of times on the quiz because I didn't take in or think about the other distances that go with this equation. But we have this distance here as it's falling, but we also have the distance up here. It's off the top of the screen of the rocket as it goes up. So that we still have that 1,000 meters as it's going up. So this is 1,000 meters as it's going up, and after the rocket, the engine cuts off, it still goes up another 1,225 meters. So we have to add these two together to make 2,225 meters. But if we look at the diagram, it's not going up an extra 2,225 meters, it's going down. So we have to make this distance negative. And now we're just going to use our kinematic equations. And so this is 0, so we can just X that out. So Vf squared equals, final velocity equals the square root of 2ax. So if we just plug everything in, that will equal 2 times 225. And then, if we calculate that, we should get 209 meters per second. And since the rocket is traveling downwards right before it hits, we want to make this negative. So our answer is negative 209 meters per second.